Hello everybody, welcome to this new course on optimal control guidance and estimation. Typically it will be hovering around aerospace engineering problems and applications, things like that, but largely the techniques tricks and techniques will be very generic. So, anybody from any other discipline can also use this concept equally well. I am Radhakant Padi, working as a associate professor in Department of Aerospace Engineering in an Institute of Science, Bangalore. So, let us see some of these introduction, motivation and things like that before we go to the details of the course. This is the main objective of this particular lecture actually. So, before we start begin, some points to note. The topics covered in this course are very generic with preferential emphasis on aerospace applications obviously, because largely if you see these optimal control applications have been driven by aerospace engineering trajectory optimization problems conventionally, and we also want to kind of develop the course this way. And this course is meant to equip the students with applied optimal control system and state estimation concepts. So, as part of it we will also take this missile guidance and other aerospace vehicle guidance problems as well, which is nothing but an application of optimal control theory. That from that perspective we will discuss actually. And the topics covered, as I told, are fairly mathematical. That means somebody who loves mathematics can enjoy it very well, but if you are reasonably good in mathematics, I think we will be able to follow it well, but that is a necessary requirement of this particular course. And I also suggest all of you that you can, as the course goes along, you take a sheet of paper, pencil and all, you start kind of practicing everything yourself, then only the charm becomes even more actually. So, the topics to be covered in this particular course is first thing is some review of necessary fundamentals. It means we will talk about some numerical methods, matrix theory, matrix algebra and whatever necessary background material that will be quickly reviewed. Then followed by static optimization concepts, and that is a kind of a backbone for optimal control in a way, because even if you see one method of solution of optimal control is first to convert it to a static optimization problem and then take the advantage of the static optimization routines and all that. So, that we need to know a little bit of static optimization before we go ahead with the optimal control principle, which is nothing but dynamic optimization. Okay. So, then we will go to calculus of variations and see some of the concepts of what is this calculus of variation. Obviously, it is a very vast topic, we will not be able to cover everything, but whatever is relevant to us, I think that much we will be able to overview before proceeding to calculus of variation applications for optimal control. And that is what we will talk next, optimal control through calculus of variations. Then that will be followed by some numerical techniques to solve these variational calculus problems, which essentially leads to this something called 2-point boundary value problem. We will talk about that as the course develops actually. But that is one of the reasons why it is computationally very very challenging and computationally overwhelming rather. And then we will proceed for other techniques, recent techniques and classical as well as recent techniques to how to overcome some of those actually. Anyway, after covering numerical techniques, we will move to this something called LQR theory or linear quadratic regulator theory, and that will be followed by some overview of flight dynamics, because most of the concepts we want to use in aerospace applications. So, it is better to know some of these flight dynamics on the way. Then we will see how LQR is used for flight control applications. Okay, so, some of the application like stability augmentance and then maneuverable enhancement and things like that. We will talk about that as an application of LQR domain. Next application of LQR will be optimal missile guidance, and that is what a lot of people do using linear system dynamics, rather engagement dynamics between vehicle and target. That is what they do. The missile and target, if you take relative motion and all, using that as a constraint and then formulate some sort of a minimum miss distance problem and then solve it using LQR theory. So, those details we will talk after that. That will be followed by some of these, then we will venture into this nonlinear concept. So, after LQR, this which is largely kind of valid for linear systems, we will go and see how this similar kind of simple concepts can be extended to nonlinear problems as well, and that will lead us to this something called state dependent Riccati equation approach. Okay. And then there is a little bit further development on that idea, which is called theta d design. So, those things we will talk. Then we will quickly venture into this discrete time optimal control theory and then discrete time LQR and a very quick overview sort of thing. And that then we will follow to a very different approach which is called dynamic programming, and that will essentially lead to something called Hamilton-Jacobi-Bellman theory, very famous. And then we will see the ramifications of that actually. Okay. So, essentially the HJB theory overcomes this curse of complexity, but essentially it leads to curse of dimensionality. That is those details we will see that in when you talk about dynamic programming. And because of this curse of dimensionality, people have thought about something called approximate dynamic programming, okay, in a discrete settings and all that. So, we will also discuss that and then use this approximate dynamic programming concepts for adopt something called adaptive critic design, and that will be a little subset of that is something called single network adaptive critic design, and that will be part of our discussion next actually. Then we will venture into a different class of problems, I mean different class of formulation, which is called model predictive static programming design. And again this particular design has a huge potential for guidance applications, and we will see some of the examples actually there. Then after that we will follow to this estimation part of the story, and these are all complementary problems, estimation and optimal control sort of thing. So, we will see first what is called linear quadratic observer. Okay, so, that is from there we will proceed to state estimation using Kalman filter, and then there is an idea of robust control through the concepts of optimal control and state estimation. Once you put them together, it leads to something like robust control approach and all that. We will see about that. Then on the way we cannot forget that there is a huge branch of optimal control that is of relevance, which is called constrained optimal control. That means whatever solution we want, it need not be only constrained by state dynamics or system dynamics, but they can also contain some of these inequality constraints of control and state. So, that means your control, for example, can be bounded between certain values. So, those bounds can be incorporated here, as well as the state bounds as well actually. So, these are essentially some of these inequality constraints, and that within that formulation how do we solve this optimal control problem. So, it is possible to do, and some of these concepts we will see. Towards the end of the course, we will go to a very again a very different approach, which is called transcription method, and this transcription method is a very direct approach of solving optimal control problem. That is what I just talked, that you convert this optimal control problem, which is a dynamic optimization problem, to a static optimization problem with large variables, large number of variables. So, that is what is the problem gets transcripted to a kind of a static optimization problem, and that is why it is called transcription method. Some overview of that, followed by some little bit overview of what is called as pseudo spectral transcription. So, that is one of the things that is getting lot of attention these days, and also it is a very fast approach, in a way so much fast that it can probably be used online actually. So, those kind of concepts can be discussed towards the end of the course, and if time permits, I will also give a glimpse of the similar concepts, that is optimal control systems as applicable to distributed parameter systems, and distributed parameter systems are nothing but systems governed by partial differential equations. There are a lot of applications again, this flow control and then temperature control and flexible body control, things like that, they all fall under the distributed parameter systems, where the system dynamics is governed by PDEs or partial differential equations, which is not very common in ODE domain basically. So, how do you solve, or how do you take those problems into account, that is the topic of discussion next actually. So, this is how the course is structured. There may be very slight variation here and there, but largely we will stick to this outline of talks actually. Some of the references on the way, you can think of probably buying some of these books. Some of them are still available, especially the first one is very much available, and it is available in Indian edition as well. So, it is extremely cheap. And one of my favorite systems, favorite books for linear system optimal control is the second one. It is very clearly written, and I like it. So, you can think of buying that. And especially the third one happens to be a very classic book. Okay, if you remember, if you can notice, it is published in 75, but it is still on print, and it is perhaps the one book which is most widely referred ever in the entire control system domain, basically, not necessarily only in optimal control. So, that is that kind of an impactful book. It has never seen a second edition, but still the first edition contains enough material for everybody to kind of look at it and then still keep on learning from it actually. So, I will strongly recommend the third one if somebody wants to get into this optimal control theory and applications as well. Then there are other books which are again, there is a Dover publication, very cheap book from Stengel, talks about optimal control as well as estimation concepts. And this this AP Sage and White book is also extremely well written book. In fact, before Bryson and Hu, that was one of the very popular books actually, and it sustains its legacy as well. In fact, this distributed parameter control and some of these Hedgehoff equation concepts and all, I will take it from Sage and White actually. Alright, so there are other books as well, which is this one is another very classic book. A lot of numerical techniques are discussed very well here. So some of those concepts can be read in detail there. And there are other publications as well. For example, this J.T. Bates, he talks about this transcription method very well. He is a very pioneer on that. And then he has published many things on transcription method as well, and that is what the book talks about actually. Then there are other estimation theory concepts, and this is my most favorite book is Krasides and Jenkins, very rigorously written, very much well written as well. And those of you who want to buy some estimation books, probably you can buy this as well as Dunn Simon's book, and this is also extremely well written. However, rigorous part is much more in Krasides and Jenkins, and I also think there is a second edition coming up. It might already come up in late 2012 or something. That is my impression actually. And obviously, there will be topics taken from literature as well. That means some journal and conference publications are also included as part of this course actually. So, take a close note of all these things, and I am sure everything will be quite enjoyable experience actually. So, let us go to some degree of introduction and motivation first before we go into this math details and try to explore more. So, coming to the introduction and motivation first, very basic concepts. So, first thing is what is called a system variable. Then we talk about two type of variables. One is input, I mean largely it can be classified as something like input variable, output variable and kind of state variables. So, what is input? Input can again be like some control input, which is nothing but a manipulative set of variables that you can or we can rather vary as we wish, and then this can be computed precisely as well. Okay. But there are other class of inputs, and remember these are actually inputs to the system, which is called noise input. In other words, they do come as a common input to the system, and they do disturb the system. In other words, for example, if you go on a car, then the road conditions and all will affect the car drive. That is not a control system, but that is a noise input to the system. Similarly, when aircraft flies, then there is a something called atmospheric gust phenomenon and all. So, that will disturb the vehicle motion as well. So, those are noise inputs. Usually, they are non-manipulated, not under our control, but we have to live with that. We have to handle that, and that is how this necessity of robust control comes and all that. Then there are two kinds of output variables as well, and one is one set of output variables that you can measure by sensors, that is called sensor outputs, but there need not be something that you want to control. So, the control can be something same or different, and the variable that you really want to control the system, or you want to have a performance measure whether the system is performing well or not, those things can be described as something called performance outputs actually. Okay. So, sensor and performance output may or may not be same. Then there is something called state variables, and the state variables are nothing but a set of variables that describe a system completely. That means, we will see some examples. I mean, you might have already seen in lot of textbooks in systems theory. And state variables are there are certain restrictions. They cannot be, you cannot take more state variables than necessary. You cannot take less state variables than necessary either. There are again problems and advantages of that and things like that. Those of you who are interested can see a classic textbook on these concepts actually. Then when you talk about system study in general, and there are three categories of system study. One is model development, which can also include parameter identification in general, and typically we will not talk about that. In other words, we will assume that the model is typically available to us as far as a control system synthesis problem is concerned. In other words, as a control system designer, we will not worry too much on modern development issues and all that actually. So, we will assume that it is known to us in a way. Then there are system analysis concepts. So, that means once you have a system model or a mathematical set of equations representing the model behavior, then you essentially want to know whether the system is behaving properly or not. So, that will lead to something called system analysis, and typical example is whether the system is stable or not stable, whether the system is uncontrollable or not controllable. So, those kind of issues are part of system analysis problem. And if the system analysis output is good, that means system is behaving well, we do not want to do anything. But if something that needs to be done, then we go to the system synthesis part. That means we design a set of control inputs in such a way that the system performance is satisfactory actually. In other words, we force the system to behave as we would like to see actually, that is how. And typically we will kind of give emphasis on this type of issues, and especially on the system synthesis part of it. The analysis will be there in a weak sense, but largely we will talk about system synthesis. Otherwise, how do we actually design a control variable using this concept of optimization or dynamic optimization. That is what the main objective of this course actually. Then when there are various classification again. So, when you talk about a system, you can classify in variety of ways. One is lumped parameter systems, where there is no relative motion between two molecules of the system. In other words, everything, if the center of gravity moves, then every other particle moves in the same way, same direction, same velocity, like that. So, that is lumped parameter system. And then there is a distributed parameter system, where you have relative the relative motion between two molecules are also there as along with the whole system getting perturbed as well. So, those are the systems that can be described only using partial differential equations, whereas this fellow's lumped parameter systems can be used in can be described in using this ordinary differential equations and all that actually. Then there are different classes of systems. When you talk about continuous time systems, where the time variable is treated as continuous variable, versus there is a discrete time system, where you talk about only discrete grid points and then see the behavior at those grid points only. Then there are ideas of quantized system, non-quantized system, things like that. And there are something called quantized, means the variables are given at a discrete number, the quantity of the variable can change only in discrete numbers actually. Non-quantized is something that varies continuously. In other words, all rational numbers are also accounted for there and all that actually. Then there is a concept called the time invariant system, and there is something called time varying system actually. So, that means if the parameters of the systems can change in time, then this leads to this time varying system. For typical example is when an aircraft moves, you burn fuel, and the rocket moves, you burn fuel. So, the system sees a different mass as time goes actually. So, that means mass, moment of inertia, all that keeps on changing. And if that does not happen, then we talk about something like a time invariant system. So, you can think of roughly, you can think of it as a kind of a UAV flying under electric propulsion probably. If it is electric propulsion, there is no expendable mass goes there, it is only the charge and all that way. But then every other thing remains constant, there is no person moving there, so they do not move around, the mass remains same, moment of inertia remains same. These kind of systems can be thought about something like time invariant system actually. Then there are something like linear systems or and versus nonlinear systems. Largely linear systems turns out to be linearized systems of nonlinear systems, because nature typically gives nonlinear systems. Anyway, coming back, if somebody analyzes a system using discrete time theory as well as quantization theory, then it essentially leads to something called digital control, whereas the continuous time and non-quantized variable combination of that leads to analog control. And it so happens most of the time that we confine in courses to the first line. That means, we discuss lumped parameter systems largely in continuous time domain using non-quantized variables, assuming time invariant systems and linearizing the system. Whereas, the reality is all in the bottom actually, mostly in the bottom rather. So, the reality, most of the systems theoretically speaking at least can be described in distributed parameter systems, even though largely lumped parameter systems are also okay from engineering perspective point of view. And then there are discrete time theories typically nowadays not given that much of importance, and quantized theory as well, because computers have become very fast, and continuous time, non-quantized and all. Even if you quantize it a very, if you quantize it at a very fast rate, and then it becomes almost equivalent to that kind of a continuous time and non-quantized sense and all that. So, that is not that much of a big deal nowadays. However, time varying parameters as well as nonlinear systems are typically reality. I mean, we just can't wish it away. But unfortunately, most of the courses in classes will be talking about linear systems and all that. So, in this particular course, we will talk both linear systems as well as nonlinear system. As a whole, entire thing we want to see in totality sort of thing. So, if it happens to be a linear system, well and good, it has its own advantage and all that, but we do not want to confine everything in and around linear systems actually. Alright, so let us move on. Then very quickly, what is a linear system then? A linear system is something, some system that obeys principle of superposition. In other words, multiplying the input by any constant alpha must multiply the output by the same constant alpha, as well as this is the law of multiplication and this is law of addition as well. So, this is so response to several inputs applied simultaneously must be sum of the individual inputs to each input applied separately. So, all these things I think is a very standard things in textbooks in linear systems theory especially. So, you can I mean this course is not geared up towards that. So, I will not spend too much of time on those lines actually, but still just a very quick example. If you consider a static system, that means there is no differential equation or anything, but the system is given by this kind of equation. Typically, the very first impression that you get is a linear equation, correct? It is a linear equation, but it is not a linear system, because it does not necessarily linear unless C is 0. Actually, it is not really linear. You can very quickly see y1 if it is like that, and y2 is mx2 plus c, y1 is mx1 plus c, then y1 plus y2 is m into x1 plus x2 plus 2c. So, the 2c is not equal to c, and hence it will not satisfy this law of addition and all that actually. So, it is essentially it will satisfy everything if provided c is 0 basically. So, that means if the line passes through the origin, then it can consider that as a linear expression. Otherwise, it is a equation of a straight line. It is certainly not a kind of a linear equation actually. So, those kind of ideas typically we forget actually, or just keep it in mind. Similarly, in dynamical systems as well, if you have a differential equation and all, if it is in this form, then it is actually a linear form, because very quickly you can verify this law of multiplication and addition actually. So, if you take like alpha into x dot, and you can multiply with alpha at the right hand side and then put 2 into alpha x. So, that is part of that. And second equation is like that actually. If you take x1 and x2 and then try to validate all that, it will turn out to be like that actually. Okay. Then if you have this kind of example 2, which is actually a nonlinear system, the moment you have a bias there, it will not satisfy, and then hence it is not a linear system. And if you talk about this kind of a system as well, again it will not satisfy this principle of superposition, 2 sin x and things like that. So, again it is not a linear system actually. So, by the way, a nonlinear system by definition is something that is not necessarily linear. That means, all linear systems can be thought about as part of nonlinear family as well actually, but not necessarily vice versa. Okay. So, in other words, if you study a concept which is applicable for nonlinear systems, it is actually equally valid for linear systems as well. So, do not forget that part of it actually. And then there are some concepts called analogous systems. So, that means if you take two systems for which the mathematical representations are similar, but their physical meanings may be different. So, mathematically these systems are kind of similar behaviors, they will have similarity, but physical meaning sense they will be having different things actually. For example, in spring mass damper system in mechanical systems is very equivalent to RLC systems in electrical systems. So, these two systems as far as system theory is concerned are considered as analogous systems. So, the math theory and all that will be very similar, it is the physical interpretation that needs to be different actually. Alright, so now coming back to the some differences between linear systems, nonlinear systems, some similarity, blah all that thing can be summarized something like this. And this is very easy to see that nonlinear systems are more realistic, and linear systems, as I told, usually do not exist in nature. All that we do is math simplicity, and you take Taylor series expansion and then forget the rest of the series and keep it only up to linear term. So, that is certainly an approximation to reality. Then nonlinear systems they are typically more difficult to analyze and design, okay, but linear systems are usually simpler in those aspects. So, the linear system, there are a lot of tools already well developed, and here tools are getting developed, they are partly done, partly not done. So, there are a lot of scope for doing further research as well actually. But the main difference what you see in for nonlinear system, the difficulty starts from here. It tells okay, the system can have multiple equilibrium point. It's very easy to give examples. For sake of time, I will not give that. But suppose you take let us say x dot equal to like x cube minus x, let us say something like that, then it is if you take x dot 0, then it is x equal to 0 and plus or minus 1. It will all satisfy. So, in equilibrium sense, you will have minus 1, 0 and plus 1, all these things are candidates actually. But if you take a linear system, that is not a choice actually. You will always land up with a single equilibrium point, and that equilibrium point happens to be origin actually. And okay, now the more difficult is the system stability depends on initial condition as well for nonlinear system. So, it is not that you have only multiple equilibrium points, but the system stability behavior itself will change depending on what equilibrium point you are talking about. Around that the system can be stable, around some other equilibrium point it can be unstable as well actually. That kind of behavior is typically not seen here. The stability nature is in fact getting independent of initial condition here, because you have only one equilibrium point, and whether the system is stable or unstable does not necessarily depend on that equilibrium point. It does not actually. In fact, if your system is stable, it is globally asymptotically stable, I mean globally exponentially stable rather. In other words, no matter wherever the initial condition is there, the system is stable means for all those points initial conditions, the trajectory will develop towards 0 actually. If it is unstable for every point other than that equilibrium point, the system trajectory will go to instability or go to infinity actually. So, those kind of behaviors are not seen in nonlinear system. They are critical. It depends on the equilibrium point as well actually. Then there are concepts called limit cycle, which is a kind of a self-sustained oscillation. There are concepts of bifurcation. In other words, this number of equilibrium points and their stability nature do not stay constant. They can vary with parameter values as well, and especially if it is a time varying system where the parameter values are changing, then you can essentially lead to this bifurcation issues and all that actually. Then there is a concept called chaos, and then chaos are very small difference in initial condition can lead to large difference in prediction. In other words, if you have a very small two initial conditions that are very close to each other, but they are not identically same, then if you propagate the system dynamics for some time, then the behavior will be very different. The dispersion will become wider and wider actually. And to a point very quickly you will see that difference blowing up. See, in other words, the system simulation is no more reliable actually. And very common example of chaotic system is weather systems really. So, that is the short duration weather prediction becomes easy, the long duration becomes difficult, because no matter how much good instrumentation and computation you can have, the system being chaotic, you cannot propagate the system dynamics or the system model for a long time and then tell your trajectory being reliable and all that. So, that is the problem of a chaotic system actually. And also there are other issues like frequency and amplitude can get coupled, and then you have associated problems with that. So, you cannot take sinusoidal signals and then analyze only in frequency and amplitude relationship and things like that. So, there are problems with that. Frequency domain analysis does not typically hold good here. So, in other words, if you see a frequency domain analysis, especially using this Laplace transform and things like that, these are typically very for linear systems only. Do not forget that part actually. So, when you talk to nonlinear systems, Laplace transforms or even Fourier transforms and things like that are typically not valid there. So, you lose this frequency domain luxury or frequency domain interpretations, and then directly you have to deal with time domain only. Okay, so, that is that's how the nonlinear systems are actually. Then a quick overview of what is classical versus modern control. These are all little bit old concept. Largely classical control is developed largely between First World War and Second World War. Modern control, what I call as linear modern control, this x dot equal to x plus bu sort of thing, that is developed between these things after Second World War largely. Okay. And then typically these are frequency domain analysis, whereas these are time domain analysis, and classical control is based on single input single output models, whereas modern control is based on multiple input multiple output. And remember, optimal control theory is all based on this modern control concepts actually. Okay. So, we'll largely this course will kind of hover around this modern control concepts actually. So, there are other things as well. You can read some of these things. The very good reason why this classical control is still popular is is because of this issue. There is something called gain and phase margin concept, which is very well defined in classical control domain, where people get comfortable with the robustness properties of the system on the design actually. So, that is typically not available here, even though in a phase margin sense you can talk about time delay margin. In gain margin sense, there is some issues there actually. So, it is not extremely well connected that way, but things are under development as well. But where this thing comes into big way is something called controllability and observability issue. In other words, if the system is controllable, then only it makes sense to kind of go ahead and find various control design schemes that are and then evaluate them. If the system is not controllable, then it implies that no control system is going to work, no design is going to work. So, it is better that we do not waste our time actually. Similarly, if it is system is not observable, then no observer is going to work. So, there is no point in aiming for an observer and or an estimator and things like that, and then struggling and wasting our time and all that actually. So, those are concepts that are available in the modern control domain only. And the big point is we not only see this classical control is largely stability based theory, and it is actually whether the system is stable or unstable. Okay. Whereas, in the modern control part of it, I mean we can also talk about something called optimality. In other words, in what sense the control is optimal, whether it is minimum time, minimum distance, minimum what actually, you can talk about that, maximum profit. Okay, all sort of things we can discuss in a very neat sense actually from the modern control perspective, and that is where optimal control comes into picture actually. Alright, so some of the benefits of advanced control theory, first of all it is a MIMO theory, that means multiple input, multiple outputs. So, that essentially leads to lesser assumptions and approximations. So, we do not have to ignore this cross coupling effects and all that, you account for that and then design your control actually. Then there are concepts of simultaneous disturbance rejection and command following, that means there are typically conflicting requirements. Okay, we have to reject the disturbance and assure that command is being followed. So, that is typically a kind of conflicting requirement, but can be done because you are not ignoring the cross coupling effect and you are taking power of modern math and things like that. So, it is possible to take into account all that. Then we can also talk about robustness issues in presence of parameter variations, external disturbances, on model dynamics or neglected dynamics or inaccuracy of parameter variables, things like that. Then even bigger things you can talk about something called fault tolerant control, that means if your system is under operation, your aircraft is flying and then you have developed some fault in actually, in other words this actuator gets stuck and all that. So, how do you still make sure that your aircraft lands or still make sure that your system behaves in a little tolerable way at least. So, it is a very big implication if you talk about let us say nuclear power plants. Then if something goes bad, it should not really lead to a catastrophe or a disaster actually. So, those kind of control system can be thought about, can be analyzed, can be developed and all using this advanced control theory. Then there are concepts of self autonomy, and some of these things we will see that. When you talk about guidance, the guidance is essentially leads to the self autonomy sort of concept, where the algorithms and all are designed in such a way that there is intermittent human intervention is not necessary. Once you fire it and then the logic takes over, then the sensors are integrated to the actuators and the sensor information will be processed to the computer and it will pass to the actuator directly actually. So, then the system is autonomous, I mean you really do not have to control anything, you do not need to bother about that as well actually. So, those are the concepts for autonomy, and there are very challenging research problems as well. For example, if you are some unmanned aerial vehicle UAV flies and then you have a camera there, then how can you make use of the camera photographs so that you can sense an obstacle and avoid it actually. So, those kind of thing you do not have to manually turn it right and left and then go and all that. So, it will take care of that itself. Similar concepts are there in robotics as well and things like that. So, it is a big field, and typically when you talk about autonomy, this vehicle guidance comes into picture, and here we are going to see how to design guidance schemes using optimal control theory. So, essentially optimal guidance schemes actually. So, why nonlinear control in general? There are certain benefits. First thing is we can think about improving the existing control systems, and some neglected physics can be accounted for, and then there are something like some explicit accounts of hard nonlinearity versus strong nonlinearity. Okay, what is hard nonlinearity? This talks about discontinuity in derivatives. For example, saturation, dead zone, hysteresis, all that. Those are nothing but hard nonlinearity that can be accounted for. Then there are strong nonlinearities, so essentially higher order terms in the Taylor series. So, that kind of both the things can be handled here actually. Okay. Then it can directly deal with model uncertainties as well, and sometimes it can lead to design simplicity as well, and that is a little bit surprise, but it turns out to be true. In other words, if you go through linear control system, the theory may be easy, but remember it is locally valid. That means you have to really go for designing a set of nonlinear systems everywhere that is of interest to you, and then you talk about stitching them through something called gain scheduling. Okay. So, that gain scheduling process turns out to be quite challenging. It is quite cumbersome. It is also problem dependent. It is discipline dependent. It a lot of exposure comes, and a lot of your prior experience will be helpful. And if the system goes through a design iteration and the system dynamics changes, then you have to repeat the entire exercise. So, those kind of ideas are not necessarily true when you talk about nonlinear system control in general basically. And it can also lead to better performance optimality. So, if you a branch of nonlinear control which can be designed through optimal control and all that, then obviously you can talk about performance optimality actually. So, that is another bigger advantage coming into picture. So, in general techniques of nonlinear control can be thought about many things. First thing, very simple, in a if your state space contains 2 or at the maximum 3 states, then you can think of something called phase plane analysis. In other words, you plot different states x1 versus x2 or x1, x2, x3 and eliminate the time part, and that will have certain meaning actually. That kind of things are called phase plane analysis. Then there is a branch called Lyapunov theory based thing. So, you define a positive definite function, and if the derivative of that time derivative of that turns out to be a negative definite function, then system is stable, and those concepts fall under this Lyapunov theory and things like that. Okay. And I mean this something called differential geometry based thing, otherwise known as feedback linearization. And there are intelligent techniques as well, using neural network, fuzzy logic, genetic algorithm, things like that, biological inspired computing, and much more actually. Then there are concepts of describing function analysis, and lastly, but hugely, I mean we are hugely concerned about this, which is called optimal control theory. Comes from this variational optimization or dynamic programming approach, etc., like that actually. That is where our focus will be for this entire course actually. I mean just a comment before I move on, if somebody is interested in Lyapunov theory and differential geometry based control theory using this feedback linearization, as well as Lyapunov theory based this backstepping analysis and things like that, you can probably refer to my first course, which is already available under this NPTEL program actually. Alright, so what is this optimal control? So, for in a nutshell sort of thing, and to understand that, if you see any classical control system book, probably you will come across this kind of a diagram, where this G of S is supposed to be a system plant dynamics, and you have something like a output, and this output needs to be a kind of tracking problem, since it output has to go to R of S. That means C of S should approach R of S with time. So, that means you have error signal there, and then this error signal is manipulated in a control gain, and that is fed back to that. So, in a control and plant together sense, this G of S comes into picture. You have this unity feedback or non-unity feedback and all sort of things there. So, this is a very standard thing actually. So, essentially if you look at it, this is nothing but a stabilizing control design problem sort of thing. You design a control gain in such a way that the closed loop plant dynamics, whatever you see here, is stable. In other words, it drives to 0 actually. All that things are fine. I mean, no questions on that. But if I ask a little question that what is R of S, most of the books will turn out that okay, this R of X are nothing but this step input, ramp input, and all sort of things actually. Typically, those step input, ramp input, parabolic input are certainly not reference signal for a plant to operate. So, for any realistic system, if you just confine yourself to those kind of signals, then obviously you are not going to go anywhere actually. But still we want to test our control system for that. The reason being, any arbitrary signal can be actually decomposed to this I mean kind of constant signal, then ramp input and all sort of things using Taylor series actually. So, that is the backbone why it is done. So, if you have any arbitrary signal, if your system behaves well with respect to, let us say, step input, ramp input and parabolic, that means you have actually testing for first 3 terms in the Taylor series. That is why it is done actually. But okay, moving ahead, in other words, what is the RFS that will lead me for system optimization, overall goal to be achieved? That means, that is where this RFS will play a major role, because if I have to guide a missile, then I have to guide it towards the target. Once the guidance is part is taken care, that means RFS is designed well, then it will be tracked actually. But what is the problem that how can I do that actually? So, this RFS come up with a value for RFS actually. So, this is what I want to talk a little bit here. So, if you that is the thing, question is what is RFS and how to design it, and unfortunately many of the books will remain completely silent on this. But think a little, and if you just think about doing this actually, okay, you take the similar output sort of thing, and then you design an RFS in some sort of outer loop sense actually. And that is typically done in using some optimization criterion. That means, if you are running a power plant, then your overall load should be at a particular level for your system to operate nicely. If you are talking about a missile guidance problem, your missed distance has to be 0 at the end. So, all sort of things are nothing but optimal control problems. So, this is the loop that you are talking about in designing here in optimal control actually. And what are the summary of benefits for using optimal control? And first of all, a variety of difficult real life problems can be formulated in the framework of optimal control. Do not think that optimal control is just another approach of solving actually. The many difficult problems which cannot be solved otherwise using any of these Lyapunov theory based techniques or feedback linearization based techniques and all can be actually handled very well using optimal control. That means, it actually gives us a very powerful technique or powerful platform to handle those problems actually. And then state and control bounds can be incorporated in the control design process explicitly. Typically, it is not true in stability based design. In other words, you design a system, stabilizing controller and evaluate it using this bounds and all that. If it does not, then go back and retune it, and the tuning process can depend on your experience and all that actually. Here we are not talking about that. State and control bounds, if it is known a priori, then those can be explicitly incorporated while designing the control itself. So, that is that's a big departure philosophically. Then obviously, you can also incorporate optimality issues for a variety of advantages. For example, minimum cost, maximum efficiency, and then it will lead to this non-conservative design and all that actually. That is a big advantage. That we can actually talk that the controller is optimal in this particular sense. Okay, so, that we will be able to discuss as well. Then essentially it also, if your optimal control can be solved very fast, then essentially it leads to some trajectory planning issues can be, essentially optimal control is nothing but a trajectory planning issue basically. So, how the trajectory evolves over a period of time. That means, the only problem there is a computational problem. Now, the computational problem is taken out. In other words, there are techniques which you can use it for solving it very fast. Then essentially it amounts to that trajectory planning issues can also be incorporated into guidance and control design actually. That is nothing is this kind of big advantages are not possible in the stability based design actually. So, what are the difficulties? These are all nice features. So, these are the benefits part of it, but what are the difficulties? The difficulty is very fact, it is a kind of open fact or it is known to everybody that optimal control problems are computationally very intensive. And do not think that your modern computers can solve it, they are nowhere close. Even the supercomputer of today is nowhere close to solve a real good trajectory optimization problem in real time actually. So, these are actually computational difficult problems, and hence they are difficult to solve in real time as well. Now, the question is can the computational difficulty be avoided at least to some class of systems, class of problems and things like that. So, that it can be actually useful for real time applications. Okay. And the answer turns out to be yes, and we can do that for a variety of things. And the first thing is LQR problems, traditionally all done in 60s and 70s and things like that. So, it's but the system has to be linear first of all, and linear time invariant most of the time. So, then only you can think of using this LQR problem. There also you need to solve something like a Riccati equation, which may or may not be solvable online if your number of states are more actually. But for a reasonably decent practical application, you can think about using LQR technique, and the Riccati equation can be solved online, and that is what is SDRE method actually essentially. So, this STRE method is a little more than that, obviously we will talk about that when you go there, but essentially it amounts to solving a Riccati equation online basically. So, that is what it is. Theta D tries to avoid it, it kind of gives you something one Riccati equation offline solution and a bunch of Lyapunov equation online solution. It has its own computational advantages actually. Then there are other techniques, pseudospectral method, adaptive critique, this MPSP method and things like that. So, these are the things that we are going to talk in this course as well. Okay. So, there are I mean all these things that I am putting here is actually we will talk in detail as we go along actually. So, what are the key components of an optimal control? Formulation, mathematically speaking, first of all it needs a performance index that needs to be optimized. Okay. And then there has to be some sort of appropriate boundary condition, and essentially when somebody talks about boundary condition, it amounts to initial and final conditions. So, we have a set of initial conditions and we have a set of final conditions, and again both can be either soft constraint or hard constraint. That means, if you talk about my initial condition value has to be equal to some value, or finally my mesh distance has to be equal to 0. So, those kind of demands are hard, and hence they are called hard constraints. But if you talk about okay, mesh distance can be minimum, I mean I do not really bother about it is 0, but it is within some let us say 5-10 meters and all that, but I am not very particular that it has to be exactly 0 or exactly 1 meter, things like that. Then it amounts to something called soft constraint actually, and both are possible in this framework. Then there are path constraints, and as I told, first thing first is the system dynamic constraint. Okay. So, every system has their own dynamic equation, and that is accounted for explicitly as a set of path constraints actually, and they can be nonlinear in general actually. So, then there are state constraints and control constraints, and as I told some time before, they can be inequality constraints actually. So, all these things can be incorporated as part of the problem formulation itself basically. So, mathematically speaking, it amounts to like finding an admissible time history of control variable within this initial time to final time, which causes the system governed by this set of nonlinear equations. Remember, this is a nonlinear set of differential equations with n number of states, and time varying as well actually. So, it is actually non-autonomous set of systems where time explicitly appears in system dynamics, that is also possible. Most of the system will not have that in our modeling and all, but even if it is there, it is possible to account for that. So, essentially it amounts to finding the control variable, accounting for this system dynamics, and then not only that, it will find a solution, it needs to find a solution for an admissible trajectory. Then the state variable x of t, whatever it turns out, it has to be admissible as well. And on the way, it has to minimize or maximize a meaningful performance index, and a performance index in general can be given something like this, but it is not the only form. It can you can design your own own cost function as well, also called as cost function. It is either you can talk about performance index or cost function either way. And this also has to satisfy certain appropriate boundary condition. So, all these things has to be part of the formulation itself, and if something is missing, then obviously it is not a optimal solution actually. And personally speaking, I mean in a personal bias sense, I think satisfaction of these constraints are the biggest advantage of this optimal control theory, and as a byproduct we also optimize certain cost function and all that. So, that is that is my opinion actually. So, there are certain some examples of meaningful performance index in this framework. You can think about some minimum time problem, then it is nothing but minimizing Tf minus T0. So, I can in this platform I can think about putting this, okay, that one I can take L equal to 1 and phi equal to 0, and I can talk about a minimum time problem. And minimum control effort problem can be thought about something like U transpose RU, and U transpose RU turns out to be something like R1 times U1 square plus R2 times U2 square, things like that. Eventually, if you minimize that, it will lead to everything being 0 or close to 0. That is where you get minimum control effort. Also, if you think about like let us say minimum deviation of a fixed value, I mean state should be having minimum deviation from fixed value, and also you want to have minimum control effort. You can think about this kind of problems as something like helicopter hovering problem, for example. Then you can think about this x is the position x y z, and then this should be a specific location c, and that is what you want to minimize. This is a quadratic term, everything I mean this is something like x minus is an error quantity sort of thing, So, you can take up that term, and then along with that minimum control effort can also be there. And also you can give relative weights here, which I have not given, but if you think about that, you can give some relative weight, something like Q here and something like R here, and then there are some requirements that Q has to be positive semi-definite and R has to be positive definite actually. Okay, so these kind of things are also possible, where you can talk about relative weightage being assigned to two different terms actually. So, those things are all possible here. Okay. Then this okay, Y state estimation. So, also remember there is a part of the course talks about state estimation, and there are certain needs actually. First of all, the state feedback control design needs some sort of a state information for control computation. You need state variable for that, and your sensors may not give that. So, you need some sort of estimation technique there. And okay, why it is not not there, in other words, all state variables are not available. There can be various reasons. Some possible reasons can be something like non availability of sensor, or maybe the sensor is available, but it is expensive. Okay, and then it is also not a possible candidate. Okay, and then sometimes the quality of sensors may not be acceptable due to noise. That also is a concern. So, any of these issues can tell you, okay, I will not be able to use all sort of sensors to get my all state variables. Okay, so then we go to this observer theory, and the state observer essentially estimates the state variable based on the measurement of some of the output variables as well as the process information. That is critical actually. They are not just dependent on the output variable only, which is actually sensor output, so given to us from sensor values, but it will also account for something like system dynamics. So, that is where the process information comes into picture. So, accounting for all that, it will try to predict, which the prediction becomes much more kind of robust actually. So, what is the main aspects of estimation? There are different things. One is prediction, you have to predict in the future. Then filtering, current value, whatever it is supposed to be, you will find it out, that is called filtering. And then smoothing, that means if the process is over and you go back and see what should have happened and things like that process is called smoothing actually. So, the three aspects of estimation is prediction, filtering as well as smoothing actually. It can also take care of limited inaccuracy of system modeling. In other words, because you are typically relying on estimated states, so this sensor information is going to help you even if your model is inaccurate actually. Okay. So, that kind of thing gives you a little bit additional robustness actually. And this estimation can also be used for parameter estimation techniques, or it essentially useful for system identification as well. Okay. So, okay, you can think of some other applications of estimation, which is okay. First thing is you can think about something like model development. As I told, you can estimate the parameters, so that is part of the model development. And you can also talk about state parameter estimation combined actually. So, that can be thought about that. And people are using that actually in fact. So, estimation techniques, especially Kalman filter and all, are extremely useful for both state estimation, parameter state estimation combined, and they use other applications, huge number of other applications as well. As you go along, we will see that some of these. It can also talk about something like fault detection and identification. There that is part of this reconfigurable control if you think of control theory point of view. But essentially, if you simply want to have an information where the system is going fault, where is the fault where does the fault lies and when it happened and things like that. So, that can be falling under this FDI, what is fault detection and identification. Okay, so, one branch of reconfigurable control leads to this relies on this FDI concept. That means, I will detect where the fault lies and I will identify that properly, and then there is a revised plant model for that, and then using that model I will resynthesize the control actually. So, that will go that way actually. So, it is possible to do this fault detection and identification using estimation concepts. Then there are estimation of states and other related systems, especially non-cooperative systems and exogenous inputs and things like that can also be there. You can very it is related to aerospace problems, especially for let us say missile guidance actually. So, you need some target information, but target is not going to declare its position or velocity or intention to maneuver and things like that. So, this is something that you have to estimate as part of your sensor measurement and all that, and that is an integral part of requirement actually. So, target state estimation, without target state estimation, missile guidance probably has a very little significance actually. So, that is where you need these estimation concepts to make your system, overall system work I mean as per your requirement actually. Alright, so there are applications as I told, first application in guidance and control of missiles, and essentially I am talking about applications of optimal control and estimations on both actually. Okay, so first thing is missile guidance and control. So we required several reasons. The first thing that we require is rapid and precise command response, and it should also take care of system limitations. For example, the missiles do not have large fins for small radar signatures and all that, and they can be tail control also. That means it leads to this something called non minimum phase systems and all. So those are the system limitations that you have, which needs to be accounted for, and it can optimal control can account for actually. And then there are concepts called disturbance rejection. For example, wind gust, motor burnout, state separation, things like that will lead to this system dynamics getting disturbed as it operates. It has to tolerate all that actually. Then the prediction of target behaviors through state estimation, I already explained about that actually. Then moving on in aerospace domain itself, we can take some of these concepts and then talk about a lot of these UAV application these days. And first of all, UAV autonomous level, you can think about waypoint guidance, where you can define this waypoint 1, 2, 3, 4, and the vehicle has to move around all these and come back, things like that. So those kind of autonomy can be brought in. And then there are automatic takeoff and landing algorithms, where that has to be autonomously done. Then there are collision avoidance problems, where it flies and then tries to avoid collision either for known obstacle or unknown obstacles on the way. So those kind of problems can be handled using optimal control theory. Then you have this formation flying issues. So that means a number of vehicles have to fly in formation, a number of robots has to go in coordination, things like that. So those can be handled. And then cooperative missions, where large number of different small systems have to operate cooperatively. Those kind of with and without leader formulation and things like that are available. So those can be handled as well. Then there are aircraft flight control issues as well. They can think about something like a fly-wire system, where there is something like the open loop system is unstable, but there is part of the feedback which is automatically done irrespective of pilot input and all that, where that will make the system stable. That is something called stability augmentation. Then you have this maneuver enhancement things are also possible using feedback theory, that kind of thing. And especially this cruise control and all in stability augmentation, you can think of using LQR theory and things like that. That is actually done in that way also. LQZ theory essentially, which is LQR theory plus Kalman filter and all that, that way. Then there are concepts for load elevation and then the structural mode control and then flutter margin augmentation, things like that. So there are enormous number of problems, enormous challenging problems rather in aerospace engineering, and especially in other engineerings as well actually. I am not kind of confining only to aerospace, but you can think about many other problems like vibration control problem, flow control and all that. It is equally valid for mechanical civil engineering problems. You can also you can think of power system optimization, electrical engineering problem. There are MEMS problems, there are nanosystem problems, things like that, which are very amenable for optimal control application, including probably biomedical engineering as well. Actually, people have actually used that for solving cancer treatment and things like that. So this is all I want to talk in this particular lecture. So there are enough motivations for us to go ahead and look all details of optimal control theory in general. But before moving further, we will talk some of this review of some of the other concepts, so that we will be feeling comfortable actually. All right. So this is the part of this lecture. I thank you very much. Thanks a lot. Bye.